Hey everyone, welcome to Simulacra. I'm Bryson, and today we're doing a different style of video. We're building in public. So I'm building a decentralized financial application that allows users to interact with Bitcoin, Ethereum, and gold and silver stablecoins. So I've done some researching and ideation, brainstorming sessions to determine what kind of app I really want to make, what should the functional and non-functional requirements be. And so we're going to start building, and I might as well build on YouTube in public with all of you so we can go through the trials and tribulations and wins and losses of building anything that users can actually use. So we're doing the first session today, which is system design. We're going over the non-functional requirements, the functional requirements. We're going to go into the APIs and the core entities of our app that will influence the data flow on our app, and we're going to build the full wireframed out system design of the application. And then we'll go into some deep dives in different parts of the application, basically to see where we can improve in regards to scalability, redundancy, fault tolerance, compliance, making sure our app is secure, and things like that. And we're also going to talk about some tools I'm using as we get deeper into the development. A major tool I'm using being Foundry for smart contract development and testing. Smart contract development and testing is super important, and Foundry is a really good seamless tool for developing your smart contracts. And so we're going to get into system design today. This is the February 12th, 2026. It's about 11 a.m. Eastern Time, session one, building a decentralized financial application. So I hope you enjoy, and let's get into it. Okay, so system design is going to be extremely important, especially in the age of AI, where honestly, being able to code in specific languages is not really going to be as important as much. The ability to think about a system holistically, how it can scale, and how it can handle different consistency or availability strains is extremely important. And so a good framework for developing a application or a feature for an application is having non-functional and functional requirements that need to be satisfied. And then once we have non-functional and functional requirements, we can start actually developing the different aspects, data flow, API of our application. And so let's start up here. We're going to first develop a little framework to help with getting a clearer sense of how to go about thinking about system design. So, up top, we want to have the primary goals, and these are going to the primary goal is to satisfy both of our non-functional and functional requirements. Cool. So, primary goal, we want to satisfy our non-functional requirements, and then we also have a primary goal of satisfying the functional requirements. All right, so you have your non-functional and functional requirements. And basically, a good way to think about these is that the non-functional requirements is what is the system able to do, and the functional requirements is what is the user able to do. And so that's a good way to break up both of these, and you can get a clear picture of exactly what your app is doing and why it's doing it and what requirements is it satisfying. And so we can think about systems design in 6 steps. First will be requirements. These are our functional and non-functional requirements. And then the core entities. The core entities of your application would be things like, if you think about Twitter, the core entities of Twitter are the user, the tweets, the feed. And so the core entities are things that make your app your app. And so we'll go into these a little bit later. And then next, you have your APIs / interface. And your API is interfaces. How is your application interacting with other applications? How is your application interacting with other applications? And what sorts of GET request and POST request do you need to have in this application? Next is your entire data flow for the app. Data flow, high-level design, and then you have your deep dives over on the right. And so we can draw arrows to these different aspects of system design. And so this is a really good framework for understanding how to develop applications. And so as you can see, we have requirements, core entities, API interfaces, the data flow, high-level design, and deep dives. And so if we start over here, we can see that not all of the components are touched on by the functional and non-functional requirements. And so if you go here, we want our requirements to both satisfy our non-functional and functional requirements. And so we will start with our requirements because they're the foundation of our application. Later, when we get into the high-level design and the deep dives, these two will allow us to draw back on our non-functional and functional requirements to develop the wireframe of the app so that we are good to go by the time we start coding. And so I have functional requirements that I already brainstormed for this application. So we're going to write some of them out now and start getting into the nitty-gritty of the system design. So let's go down here. Let's say functional requirements. So functional requirements. So for this app, we're developing a decentralized finance application that allows users to view the balances of crypto addresses that they post into the app, and also allow users to fund what I'm called community pools, which is just a community fund of different tokens, whether that be Bitcoin, Ethereum, or the stable coins for gold or silver. And so the point is to develop a kind of communal app that allows users to view their balances from across their crypto addresses in one hub, and then also they have the ability to fund smart contracts called community pools. These community pools will hold funds, allow multiple owners to be owners of one community pool, and so on. So we're going to start getting into some functional requirements that I thought about. So first, users should be able to create an account using username, email, address, password, etc. So that is a first requirement. Second, users should be able to see the balance of their BTC, their Ethereum, and their gold / silver stablecoins by posting a crypto address into app. We will also want the users to be able to see that balance in one place. So I have a massive problem as a user right now. I have Bitcoin across different applications and exchanges and cold wallets. And so it would be very convenient for me to be able to post all of my addresses into one application and see my total balance of Bitcoin. Okay. We also want the users to be able to deploy a smart contract. And if you noticed, all of these phrases start with users should be able to. You have to remember when you're developing the functional requirements for your app, you want to be user focused, user centered. So users should be able to deploy a smart contract that allows users to fund the contract with tokens. And those tokens are the tokens that we were talking about earlier. So what else do we want our users to do? Well, we want to make sure that only the owners of those contracts can actually withdraw funds from the contract. We wouldn't want anybody just being able to withdraw those funds. That would defeat the purpose of a secure community pool. So user, or if there are multiple owners of a contract, only users, and in quotes we can put owners, in brackets we can put owners, should be able to withdraw funds from the contract. So these are some of our functional requirements. Remember, when you're really starting to develop the skeleton of the application, you don't need to go crazy. You just need to make sure that you are satisfying the main overarching goals of your application. So now we're going to get into some non-functional requirements. So let's go with non-func requirements. I don't feel like writing all that out, so we're going to just start with that. And so for non-functional requirements, like I said, you want to make sure that you are thinking about what should the system be able to do based on these functional requirements. What should the system be able to do? And so I did some brainstorming earlier, and we're going to break down non-functional requirements into different areas. And you can break down these areas based on the scalability of your app, the latency of your app, what latency concerns do you have, what security concerns do you have, do you have any fault tolerance concerns, or where does your app need redundancy, where does it need to be durable. And so these non-functional requirements might be long, and you might think that they're pretty detailed, but they're very important in terms of the underground, the back-end function of your application, and overall making sure that your application is very scalable and always consistent or available for your users. Let's start with scalability. We're going to assume that this application is going to have a good start. Why would we not assume it's not going to be a successful application? So we're going to make sure that the application can handle a good amount of daily active users. For scalability / latency, those two things go hand in hand. And let's bring this up so everyone can see. So for scalability and latency, the system should be able to scale to support, let's say, 200,000 daily active users. And let's say that 10% of those users will be concurrent at peak. For added granularity, we can add 1 million requests per second. So already we are thinking about how can this application scale what happens if one day I make a viral piece of content for this application and 150,000, 200,000 people come to the application? What if 10% of those 200,000, come to the application? How are we going to handle those scaling issues? So next, in terms of scalability or latency, I want users to be able to have a lot of optionality in terms of how many crypto addresses they can post, how many watch crypto addresses they can see the balance of. Because, I have a good amount, but everybody is different and some people may have way more than me. So I want to make sure that my users are covered and not capped really prematurely at a number of addresses that they can see the balance of. So the system should be able to, support up to 50 watched addresses per user. And 50 may be a lot, but when you're talking about people who are traders, maybe whales that have a lot of assets in cryptocurrencies or stablecoins, then having 50 different accounts is maybe not that crazy. But I'm giving my users wiggle room, and so they don't get capped. Also, so next, the system should be able to return these balances to the users very quickly. We don't want users waiting 15 seconds for a balance to come back. What if they really need that in a pinch and in a hurry? Then we want to make sure that we're getting this information back to our users. And that's where later we'll talk about more in terms of when you're building applications and CAP theorem. Your consistency of your data and your application, or the availability of your data and your application to your users, and certain trade-offs choosing between the two. So we want to make sure that our users are getting these balances from these watch addresses in a decent amount of time. So the system should be able to return balances under, let's say, 3 seconds. 3 seconds. 1 Mississippi, 2 Mississippi, 3 Mississippi. I think that's a good enough time. If you post an address, the balance comes back to you in less than 3 seconds. And this is where, when you're building scalability and you're going into your non-functional requirements, you can get very granular in terms of thinking about how users are interacting with your application. And so to help out with scalability, for instance, say a user has already retrieved this balance and they already have it on their account. And so we're going to want that balance, a new fresh balance, not a stale balance. We don't want stale data to be returned when the user comes onto the application. So on a refresh on a page load, or a refresh on a completely new sign in to the account. So for instance, we can say the system should be able to return balances under 3 seconds for a refresh page load. And then we can break that down into, also, system should be able to return balances under 3 seconds on a refresh page load and manual refresh. And so that will handle when a user is already inside of our application and just presses the refresh button. And that will handle when a user signs into our application and they need to get a new non-stale balance for their crypto address. Also, in terms of scalability, this is where you can think about things like security. And it's very interesting that different aspects of the non-functional requirements will start to influence other aspects. But this is where you can think about things like how your security affects your scalability of the application. We want to make sure that users cannot spam the application. If users are spamming the application with requests, that means that our application can be slowed down and bogged down by request, and that could be a major bottleneck. And so we want to make sure that users are not able to just spam manual refreshes for those balances that they want to see for their crypto addresses. And so, to handle this potential problem or this potential bottleneck, we want to make sure that the system should be able to, or the system should have, let's say the system should have a per user rate limit on manual refreshes. And we can get even more granular with that. We could say, let's say, I don't know, one refresh per 5 seconds. One refresh per 5 seconds per user. So that makes sure that each user only gets one refresh per 5 seconds. So they're not constantly just spamming our application with requests. That's a big way that our application could be taken down by a distributed denial of service attack or some other injection attack. So that handles a good amount of scalability and latency for the high level aspect of our application. We can definitely get into more detail when it comes to where we can also cut latency and increase the ability for a scalable system. But I think this is a good starting point for right now. So next, we're going to start on compliance. I didn't want to think too hard about compliance for a Web3 decentralized finance application, but I wanted to make sure, I think the biggest way outside of making sure databases are secure and things like that, since my application is not directly handling users' funds, it's not a wallet, and it's not an exchange, I don't have to worry about losing people's money. On the application, the funds are executed by a smart contract. They're not executed by my application. You can basically deploy the smart contract from my application, but all of your funds will live in the smart contract, and only the owner has access to the smart contract and can withdraw from that smart contract. So in terms of compliance, I mainly need to worry about anti-money laundering and knowing what kind of user is on my application. Who is my client, basically. And so we can say the system should require users to submit their, let's say, permanent / mailing address after account creation. And we can get granular with that and say at least 4 hours after account creation. So we could say the system should require users to submit their permanent mailing address after account creation. We can also make sure that we have an added layer of compliance for Know Your Client and anti-money laundering policies by saying the system should require users to submit license number with account creation. So when users create an account, they'll be asked to submit their license number, their permanent / mailing address, along with the username, email address, and password. And so that'll give us a comprehensive user profile that will make sure that our application is anti-money laundering and Know Your Client compliant. All right, so cool. Next, let's go into security. How can we think about security of our application? And I think there's two main ways, and we can get into more as we start building the app. But there are two main ways to think about security. We want to make sure that our app is secure from people who aren't even really users of our application. We want to make sure that our application is not getting botted. We want to make sure that actual humans are doing things on our application. Now that gets a little bit harder with the rise of agentic AI and AI being able to answer emails and do things like that. But still adding some layers of security is always very good for your application. And so we're going to start with the system should require users to input a verification. Let's say just verify code, and it will be sent to their email to create an account. So to create an account on the application, you're going to need to input a verification code that will be sent to your email when you create an account /sign in. And so that makes sure that there's just another layer of security to our application for bad actors. So we're going to go with another security measure. And this has to do with the actual transactions that is happening for the community pools. We want to make sure that those transactions are being deployed securely. So let's say the system should require, or the system should execute user transactions securely. And we can get into more granularity about what that exactly means, but we can say that RPC nodes are useful for this. And so RPC nodes are called remote procedure calls. And they're sort of like APIs. And they're basically nodes that are just specialized servers, and they act as the bridge between decentralized applications, wallets, blockchain networks, and other software applications. They're basically like APIs for decentralized applications. And so we can use a tool like Alchemy to handle our blockchain connectivity RPC nodes. So we'll get to this when we are ready to start doing some actual developing and testing for this application. Security, compliance, scalability, fault tolerance. So fault tolerance is a very important thing in your app. Fault tolerance is simply a system's ability to continue operating despite failure from the other aspects or components from your application. We can think about fault tolerance very simply in that we will say that our system should be able to handle failures and retries for functions, contracts, etc. And so we'll see as we are developing the functions for the smart contracts and then the test for those functions that we are going to have to go to Solidity documentation or Rust documentation to make sure that we are handling the failures and the retries. What happens when your function is called and it doesn't do what it's supposed to do? How do you handle that retry? Do you go back and call again? How do you handle the message to your users? Are you going to tell your users that, hey, this function is not able to be done, try again? Or you're going to not send them a notification? So those are some things we will think about as we develop the app a little bit more. And so lastly, but not least, there is a ton of non-functional requirements you can go through, but we're going to end with redundancy and durability. I spelled redundancy wrong. So redundancy and durability. Essentially, where does your app need to perform again and again and again with consistency at the same time so that your users get the same experience? And durability, where does your app need to be durable, especially in terms of data, so that your data is not lost and that users have access to this data with consistency or availability? So let's think of a first one. The system should be able to hold users in a database, let's say DB, for reference when logging in, KYC, know your client, and anti-money laundering. And so we want to make sure that the users that are coming to the application are being logged in a database so that A, we are fulfilling our know your client and anti-money laundering policies, but also so that the users don't have to create a new account every single time that they visit the application, and all of their information associated with their account is tied to their account. Now, all of the metadata and ABI data and other blockchain data will be able to be accessed using the transaction address or the crypto address of the community pool, but you still want users to be able to see what's happening with their features and products in your application. Next, we're going to go with the system should be able to hold user addresses after contract execution. All right, next. So what else needs to be redundant? Well, we want to make sure that when a user executes or deploys or funds a community pool, we want to make sure that those transactions and those addresses for them transactions are held in a database and users can see all of their transactions in one place. So the system should be able to hold user transactions addresses after contract execution. And for more granularity, we can say we want there to be a model or a button, a modal or a button to the block explorer so that the user can see their exact community pool or that exact transaction they just made on the actual blockchain. And then lastly, we want to make sure that the system as a whole complies with our anti-money laundering and our know your client policies. That is spelled, I said compile, but I meant to say comply. And so these will be our non-functional requirements. Not an exhaustive list, but a very good list to start off with to think about how exactly will your app function, what can the users do, and what should the system be able to do that allows your users to continuously use your app the way it's designed. So those are our functional requirements and non-functional requirements. So now that we have our functional requirements and now that we have our non-functional requirements, we need to think about something that is called CAP theory. And CAP theory is part of your non-functional requirements, but it's also going to be a major overarching theme of your application. And so basically CAP theorem says that you have consistency, availability, and partition. And a system should have partition tolerance, which basically means that the system works despite network failures. So if one part of your system fails, but another part of your system is good to go, boom, that one fails. Let's say they're connected, boom. That system can still work even though this system fails. That is what partition is in CAP theory. Now, partition tolerance is an absolute must in application system design development. We can't do without, but a major trade-off will be between consistency and availability. Consistency is that the system has consistency, meaning that all the nodes or the users see the same data at the same time. Availability means that all of the nodes or the users will always have available data, even though that data may be stale or out of date. And so as you can see, there's a major trade-off between these two, where you want to make sure that users are receiving data that is always available when they need it, but sometimes that data may be stale because it might not have been updated yet. There might have been a change to a database. Your cache might not have synchronously or asynchronously flushed to your database. There's a myriad of other reasons why your data could be stale. And so you want to make sure that you think about, all right, for this application, what is more important? Is it more important that my users have data all the time, or is it more important that that data is always consistent? And so for this application and thinking about some of these non-functional and functional requirements, I made the decision that this application needs to be more consistent than available. And that doesn't mean that we're going to make sure that the application is not giving the users the exact data that they need to, but I want to prioritize that data being correct and that data being up to date rather than that data being available quickly. For our CAP theorem, and we're going to write this down here. So let's move over here. We'll just add it down here because it's a part of the non-functional requirements. Your CAP theorem. And I'm going to say I want the partition, which is always needed in CAP theorem. The system should have partition tolerance. That means the system works despite network or node failures. As we just talked about, this application needs to be more consistent than available. We still want to make sure that data is available for our users, but we want to make sure that that data is very consistent since we're dealing with user balances and financial data. For our consistency, we want to make sure that the system should have consistency. And that just means that all nodes, users, see same data at same time. So now we have the functional requirements, the non-functional requirements. We've talked about CAP theorem, and we have answered the question of should we value consistency or availability more in this app. So now what do we want to do? Well, now we want to start developing the core entities of the application. And again, those core entities are the aspects of your application that your application cannot function without them. So if you're building Twitter, your core entities would be the user, the tweet, the feed that the tweet comes on, and things like that. So let's go into our core entities. What are going to be the core entities of our application? So we'll continue writing under here, core entities, did I spell that correctly? I did. And they are basically, a good way to think about a core entity is a noun or resource necessary to satisfy your functional requirements. So for this decentralized financial application, we're going to have core entities of a user. We're going to have your token balance. We're going to have community pool that people can fund, and that is going to be a smart contract. We're going to have the actual transactions. We want to treat the transactions as a core entity because they hold a lot of data that will be important for our user. And then we want to have the addresses is also a core entity. So the user will post the digital addresses inside of the application, which will give them back a token balance. The user can also deploy community pools, which are smart contracts, and they can deploy them, fund a community pool, and withdraw from a community pool if they are the owner. And all of those community pools and all of those executions of smart contracts will lead to the transactions. So these will be our main core entities of our application. And so from your core entities, remember, if we go all the way back to our system design framework, our core entities are next. We just came from the functional and non-functional requirements. Now it's time to develop the API and the interface. And we don't actually have to develop really super intense code for this. We're really just thinking about what kinds of things is our application posting and what does our application need to get from other applications. Thinking about APIs from a Web3 application aspect, we have to understand that apps requiring blockchain data have client-server models, and that client-server model is the RPC node. So next, we want to write our APIs. So we have to think about what exactly are users doing in our application. Well, first, they're posting addresses. So they're posting addresses to the application and receiving balances. Say v1 addresses, and it's a post request, and the body will be a text, which is a string. And that text will be the address that the user wants to see the balance of. So boom. So that's our first post request. And so now that we're posting these addresses, we have to get and return the balance. So we're going to have our get request. So we have v1, and we can have the balances of those addresses, and we can have that be the ID, address ID, which will be the address balance. So we're getting the address balance by going to the address ID and getting the balance of that address ID. And so what else are we doing? So the users are deploying community pools, which are the smart contracts that users can hold funds in. So that is another post request. And so we're going with version 1, and we're going to call these the contracts. And so our body of this post request will be the actual smart contract. So we can just say the community pool, which is a smart contract, and we can just say this is a smart contract. And saying this is a smart contract, we know that this will be written in a language that is suitable. Next, users can not only post or deploy the community pool, they can also fund it. But funding is another post request because you're writing to the smart contract. So we're gonna have another post request, and this is where we can fund the community pool. And so we have a post request, and our body is going to be the community pool, and that will also be a smart contract. And so we know that this post request is funding this community pool, and that community pool request is a smart contract. All right, cool. So what else can we do? Well, we need another one for withdrawing. So withdrawing is another write function which we are posting to something. And so what can users also do with these community pools? Well, they can also withdraw from the community pool. So that's going to be our post, because withdrawing is also a writing function. So we're going to contracts, we're going to withdraw from the community pool, and we're going to denote that as a smart contract. All right. And so lastly, what else are we doing? Well, users are not only up here getting the balances of an address ID when they post an address ID into the application, they're also getting the information on the community pool that they deployed or funded or withdrew from. So we need to make sure that when a user posts the community pool transaction ID or address ID, they get back pool data, and that pool data could be either metadata for the smart contract, it'd be ABI data, and so we need to account for this request. And we're going to say community pool, and we're going to have pool data. And so in our body, we're going to have this pool data be in a form of a string probably. It's usually ABI data for smart contracts are usually in the form of JSONs. And so under here, we can say ABI metadata for our smart contracts. And so these are some of our APIs that we can think about when developing our application. And so as you can see, the APIs don't have to be super detailed for right now. We're going to actually code out the full API and make sure it's secure, everything like that. But this is a good way to think about and visualize what exactly is your app doing and what is the data flow of your app. And so now that makes it very easy to just write out the data flow of the app based on the core entities here and your API or your interface. Now you can write your data flow. So if we go here, and your data flow can just be in a list. It can just be in a list. And so what do users do on our app? So a user creates an account, and we know we have your KYC, anti-money laundering, etc. So the user creates an account. Second thing that they do is the user can read balances of an posted address or addresses. Third, the user can deploy smart contracts, which are community pools. So fourth, the user can fill those community pools, or they can fund those community pools. Fifth, the user can withdraw community pool. And lastly, a user can see all of the information regarding the transactions for the community pool. So the user can see the recent transactions of a community pool. And this is our data flow of our application. Pretty seamless, pretty easy. And now we can get into actually wireframing and drawing out these different aspects and components of the application based on our data flow, the core entities, the APIs, and the functional and non-functional requirements. And so if I go back and scale out, this is very hard to see now, but this is a very good framework for developing applications and going about developing systems. Starting it with your requirements, going into who is actually affected, what nouns and resources is this application actually doing and using and acting upon, the different requests that my application is going to make to other applications, how data is going to flow, and now we're going to get into high-level design. And in the next video, we'll go into the high-level design and deep dives for the Web3 application. So, if you like this video, please support the channel, like and subscribe, send to your friends. I'm Bryson, and you're watching another video from Simulacra. Bye, everyone.